in about 2 weeks. Yes.
But we are like 5 chapters before the end of the lectures. I'm not sure how will we cover all of that.
You will see.
You will see.
Actually, 5 chapters.
Yes, chapter 10 to the...
Because you have not yet started the knowledge.
But these are actually supposed to be sections of the class, so we have 5 sections, which means that we cover 5.
Depends. Not always we finish one of these lectures, supposedly. Okay.
There are actually 4, not 5. The last one is just a set of problems.
Do you have any recommendation for the exam?
Any recommendation?
Because supposedly it's just like half a page for writing everything, right? Okay. That's fine.
Why is it a problem?
You realize that the camera is up.
Maybe something can go with dimensional analysis and you don't need to work.
Well, you can use as much paper as you like. I just don't want to see your calculations. As long as you find the correct result, use as much paper as you want.
So if we just write the results and give it to you?
Yeah.
Okay.
Okay.
And what if you do the same in exam?
The same in exam?
Can you do that? Can you omit some steps in the calculations?
Yeah.
Oh, thank you. Because no one has said that to me before. Everyone said that you have to show all the steps in order to get a good score.
No, I just found the answer.
Okay, great. That's really
If you don't find the answer, go.
Okay, other questions? Don't worry too much about this. Okay, so now we want to talk about nonlinear gravity.
Before we put in nonlinear gravity, in the last lecture you talked about the predictions that the spin to gravity, linearized gravity makes about the binary stars, right? So are there any specific examples which have been tested? Any specific examples of the binary stars which have been tested for the predictions?
Yes. Like for instance, Hall-Taylor.
Yeah, binary in the notes, but apart from that example.
Well, I think there are a few pulsar binaries which have been, whose period has been measured very precisely, and they are in very good agreement. Now, probably Hall-Taylor is the most famous and most precise one, but there is more than one.
Okay, so is that the most recent example that has been?
No, Hall-Taylor has been known for a long time. Maybe, I don't know, maybe 2 or 3 decades.
Is that in our galaxy?
Good question. In principle, I should know the answer. I know.
Okay. If that is known for a long time, then probably it's in our galaxy.
Probably.
Okay.
So yes, so far we don't have any. We don't have any evidence against the spin-2 gravity or general relativity. Anything that we have observed so far is in agreement. Alright, but so far we only talked about the linear version, and now we want to talk about the nonlinear version. Of course, gravity, the gravitational field can become strong. And then there is no justification for using the linearized theory when it becomes strong. Like for instance, we can have black holes. If you put too much mass at some point and to compress it a lot, we see that this, for instance, h mu nu field, the gravitational potential keeps increasing at some point it becomes on order 1, and then there is no justification for using the linearized theory. So we have to have a nonlinear theory. So we should talk about the nonlinear theory. Now let us go back for a moment to the dilettante case, when our linearized the scalar gravity theory was this T. That here we had T, which was the trace of the matter energy momentum tensor, and this was evaluated as zeroth order in phi. So now, for instance, we can ask, how would we write a nonlinear version of this theory? And the answer is that there is no unique way. From a theoretical perspective, we could do different things. We could postulate that this is the full nonlinear theory, or we could add the meaning that, so let us remember what is the definition of this. When we wrote this equation of motion, this implied that we have an action which consists of 2 or 3 parts, depending on how we divide it. So there was a part which purely depends on phi. It would give us the left-hand side of the equation, or just the kinetic term for phi. And then there was the part that depends purely on the matter field, where this T mu nu was derived from. This T mu nu or T mu nu of this matter field, and then there was the interaction that was phi times that T mu. Maybe there was a minus sign, I don't remember. So we wrote this action gives this equation. And this T mu nu, or this trace of T mu nu, is well defined. It's what we derive from this part of the action. And we could postulate that this is the full theory, full nonlinear theory. There was no theoretical principal problem with that. Of course, phenomenologically, this theory doesn't fit even a linear order. Or we could say that at nonlinear order, there will be other terms added to the right hand side or left hand side. Some extra order phi or order phi squared terms will be added here. For instance, I could say, let's add a T1 matter mu mu. Let's also include, for instance, the stress energy tensor that we derive from this part of action, or the part that we derive from this part of the action. We could add extra things that would become important at nonlinear order.
But if you are adding more terms, if this theory fails already at the linear, so why are we pursuing that?
If what?
If the theory already fails at the linear order.
Oh no, sure, yes. I'm just saying that there are these possibilities, but we are not actually going to consider them exactly because already at linear level is not an adequate theory. But I'm just saying that as a matter of principle, we could construct different theories, or which would correspond to adding higher order terms in this action. Higher order interactions of phi and matter, or higher order self-interactions of phi could be added here. There is no uniqueness. Okay, but we don't do it exactly because already at linear level we have a problem. Now let's go to the case of the spin 2 gravity. Where we had a tensor equation. This epsilon, if you remember, it was a linear differential operator, second order differential operator, and then on the right hand side we put the zeroth order energy momentum tensor. Now we want to go we want to go to nonlinear order or construct a nonlinear version of this theory. Here the situation is very different. There is no arbitrariness or ambiguity. Or in other words, we cannot just decide that we cannot just postulate that this is the full story. This equation is actually inconsistent. And the reason is that, as we mentioned, the left-hand side of this equation is identically conserved. So if I apply d mu on the left-hand side, I'll get 0. However, when I apply d mu on the right-hand side, it's only 0 at 0th order in H mu and nu. At higher orders in H mu and nu, the mu of T mu nu 0 is not 0. Why? Because we have interaction between matter fields and the gravitational field. And this T mu nu 0 was only the energy momentum of part of the constituents of our theory. For instance, there can be emission of gravitational waves. So matter can lose energy and give it to the gravitational waves. And therefore the T mu nu of just matter fields will not be conserved. Moreover, if I have some system which is gravitationally interacting, there will be a contribution to the energy of the system just from the gravitational binding energy, right? So if, for instance, if we have in the solar system, it's a non-relativistic system, there is a leading contribution to T mu nu which just comes from the rest mass of the planets and the sun. But if we want to include the subleading correction, the kinetic energy, there was potential energy, gravitational potential energy that depends on the gravitational field or H mu nu. So that is not included in this T mu nu 0. And obviously, without including that gravitational energy, this T mu nu will not be conserved. Or more generally, if you have an action which made of various fields, say I have psi and phi in my action, as long as the action can be separated into two pieces, a part which only depends on psi and a part that only depends on phi, then we can derive a conserved energy momentum tensor from this and another conserved energy momentum tensor from this part of the action, just following the normal procedure. However, the moment we add a coupling between phi and psi, some interaction between phi and psi, then this property is lost. We will have only a single conserved energy momentum tensor. So now here is a similar story. This T0 mu nu was derived from the matter action when we did not have gravity. The moment we couple it to gravity, then it will not be conserved anymore. So now what is how can we fix this problem? So one could say that, so first of all, the action that will give rise to this equation is, so there is a pure quadratic action in H mu nu, a gravitational contribution. Let me call it SG for gravitation. There was this matter, and then there was some interaction between H mu nu and T mu nu, which we said we take it to be 1/2 d4x H mu nu T mu nu 0. So now we need to have something which is conserved when the equations of motions are satisfied on the right hand side of this equation. So we can try to fix this problem, correct this right hand side to obtain something which is conserved. Obviously, we want to get something that represents the full energy momentum of the system. So one could try to do the following. Let's derive the energy momentum tensor from this part of the action and put it there. Let's call it T1 mu nu 1 because now it is linear in H mu nu. And so this is the part you should think of it as what comes from including gravitational interaction of matter fields, like the gravitational potential in the solar system. But there is also energy in gravitational waves even when there is no matter field. Like for instance, in the previous lecture we calculated the flux of energy in the gravitational waves far away from the sources. So for instance, we can also add that. This was something quadratic in H mu nu. We can ask, is this a good theory? Is it a good nonlinear theory for H mu nu? So obviously we want this equation of motion to be obtained from an action. So when I add these terms on the right hand side, I have to modify the action, right?
Sorry, what is the last thing?
What is this?
Yeah.
This is the
Your gravity action.
This is the energy momentum tensor of gravitational waves. So this is the energy momentum that I derived from the quadratic action in H mu nu. Yes.
And why didn't we add this term before, even though we had the gravitational waves?
Because we were working with the linearized theory. We wanted to find a linearized theory of gravity, while this term is quadratic in the gravitational in H mu nu. In fact, we didn't even include this term because we are working under the assumption that we have a weak gravitational field, right? So we want to consider the leading equation of motion, and even this term is negligible compared to T mu nu in the weak field regime. So we were keeping the leading contribution in the right hand side in a small H mu nu. So before the justification was that H mu nu is much less than 1. Now we want to go beyond that. We want to consider a nonlinear theory for H mu nu. That's why we cannot neglect.
But this will never stop, because adding a term of which is quadratic energy, you will have to incorporate a term which is cubic energy action and so on. It will never end.
Right, exactly. So that's exactly the problem. Now it's not. So let me just say it to others and then add a comment. So the point is that once I add these extra terms, the action has to be modified. This is an equation that is supposed to be derived from varying the action with respect to H mu nu. So once I have a term which is linear in H mu nu here and depends on the matter field, it means that there has to be some coupling between matter fields and H mu nu, which is order second order. So think of this as Sm first order, because it depends on the matter fields and the first power of H mu nu. So in order to get this term, there has to be a term in the action which is quadratic in H mu nu and depends on the matter field. And in order to get this term, there has to be a term in the action which is cubic. So this gravitational contribution that we have is give us this equation was quadratic in h mu nu. Now, if we have a quadratic term in the equation of motion for h mu nu, there has to be a cubic term here. But then, once we add these terms to the equation, then the energy momentum of just this part of the action is not conserved anymore. So we have the same problem as before. We can try to add these terms. But then we have to add new terms in the action. And this process, in principle, it continues indefinitely. I mean, up to infinite order. Now, the statement, the claim is that if you actually follow this procedure all the way, or find a pattern, you will discover Einstein's gravity. You will discover general relativity by this construction. Now, this is probably a very inefficient or cumbersome way of doing that. There are actually ways of doing it, more clever ways of doing it, in which this process truncates after a couple of steps. But one should be a bit more clever than what I tried to do here.
What if you take Einstein's gravity and linearize it and you get the same thing?
Oh, sure, if you know the answer, then... No, but you want to, the question is that whether it is unique.
Oh, okay. So is there any proof that it is unique?
Well, there are proofs at various levels of rigor. But yeah, there are, you have to make some assumptions, I guess, but there are very good arguments that this is a unique thing that you can. So yeah, there are ways of doing this process, but we are not going to do that. We want to just hint at a way of how you can construct this nonlinear theory, but not by constructing it order by order. We want to find a better principle to follow to construct this nonlinear theory. But at least conceptually, it's good to have in mind that this is conceptually what is happening. You write a linearized theory, and you want to make it consistent and nonlinear order, and the result is general relativity. Okay, so now the smarter way of getting to this nonlinear gravity is can be inspired by looking at what happens in Maxwell theory, for instance, in other gauge theory. So remember that we said this h mu nu is redundant. It has too many degrees of freedom, so we have to get rid of it. And the way to get rid of those extra things was to impose this linearized diff. So it had some extra gauge symmetry. We made a comparison with Maxwell theory. Where we had a mu and we had a symmetry. At the gauge symmetry, U1 gauge symmetry of the Maxwell field. We said that here we also have redundancy, and in order to get rid of the extra degrees of freedom, we impose that this condition has to be satisfied. As a result of this condition, the equation of motion for a mu, which was the Maxwell equation, has a similar property, which is that if I act on the left-hand side by derivative, I will get 0 identically. Which means that J nu has to be, whatever source that I put on the right-hand side has to be constant. So we can ask, how can we couple a mu to matter fields so that we satisfy this condition? So we want to write an action for A and psi, and this action should be such that when I vary this action with respect to a mu, make that transformation of a mu, it should remain invariant. So this action, how would it look like? There is a kinetic term, f min squared with a -1/4 term, and then there has to be a coupling between a mu and a current, and then there will be a matter contribution, which depends on psi. Now, if I do a variation of this gauge transformation of this a mu, what I get is d mu minus d mu alpha times j mu. Delta of s psi a is, so s psi a is this part, the coupling with the matter fields and a mu. And the way I wrote it, this change is integral d mu alpha minus d mu alpha times j mu. So how can we ensure that the action is invariant under these transformers? Let us remember that if the matter action had some symmetry such that psi s of psi plus that symmetry transformation is the same as S matter, or better, if the change of the matter action is a total derivative, it's the boundary term. Then, if we promote the transformation parameter to some localized function of the space-time, so I introduce some a of x times delta s of psi. Then the change of the action is going to be d mu of a times j mu, which we call it a Noether current, plus some boundary terms that we don't care about because this a of x we assumed is vanishing at infinity. So boundary terms are actually 0. So we had this result from the Noether theorem that if the matter action has a symmetry, then if I promote the parameter of symmetry transformation to a function of the space-time coordinate, then the change of the action will be of this one. Now we can compare these two results and see that if we want to construct an action, a coupling between a mu and matter fields, which is invariant under this transformation, what we can do is to identify these parameters, A and alpha, and identify the current that is coupled to a mu with another current. Now actually here I have cheated a little bit, or I have only worked at linearized order of coupling between a mu and current. If we want to have in principle there can be the coupling between matter fields and a mu can be nonlinear, so there will be some extra thing. But this argument is valid in the sense that at least in the limit that a mu is going to 0, you want the action to be gauge invariant, and that is enough to ensure that you want ensure that this procedure is a valid procedure to couple the matter field to a mu. There is another possibility. Another possibility is that the coupling between a mu and matter field by itself is such that that part of the action is invariant. That would be, for instance, coupling f mu nu directly to matter fields. So therefore, it wouldn't change at all. You have probably seen in QED the anomalous magnetic moment. So that's a coupling between f mu nu and the electron field. Whereas psi bar gamma mu nu psi coupled to f mu nu, and this is a dimension 5 operator, so you have to suppress it by some mass scale. Now you can see that if I want to add this coupling between a mu field and the matter field, that wouldn't rely on having coupling a mu to another current. I just coupled f mu nu directly, which is invariant on the U1 transformation. However, these kind of couplings are usually called irrelevant, so they have to contain derivatives of our in this case a mu field, or in general derivatives of the gauge field, which means that these are interactions that at long distances they become less important. For instance, the interaction between magnetic dipoles falls off faster as you go to larger distances compared to the interaction between the charges. The interaction between charges is something that you get by coupling a mu to the charge current of electrons, while the interaction between magnetic dipoles will be changed or modified by this. Okay, so now this procedure of finding a symmetry of the action, a global symmetry of the action, in the case of electromagnetism, that was the U1 global symmetry. Finding that and then promoting the parameter to a space-time variable, and then introducing a gauge field, a mu, to make it a symmetry. That is called gauging a symmetry. So you started from a matter action with a global symmetry, you introduce extra field, extra gauge field, and make that global symmetry a local symmetry. Now from this perspective, what we have done in the case of linearized gravity was something very similar. We coupled h mu nu to t mu nu, and t mu nu was the conserved current, another current that we derived from the fact that action is invariant under translations. So in a sense, what we have done when we coupled h mu nu to matters was to gauge the space-time translations. So we had h mu nu, which was invariant under this transformation. Let me like that. And then the source that we had was T mu nu, which was the nodal current corresponding to take sending x mu to x mu minus a mu. So if we want to follow that same strategy here, what we should do is to identify this parameter a mu, the parameter of our translations, which was a global translation. We want to identify with the parameter of the gauge transformation, so make it local and identify with x mu, and construct an action which is invariant under this local transformation. So this is going to be our guiding principle. We want to construct an action which consists of a gravitational part, only depends on h mu nu, and a matter part, which depends on h mu nu and matter fields, with the property that it is invariant under this local transformations, which has a name, which have different names. They are called general coordinate transformation, or sometimes called reparametrization or diffeomorphisms. Now these are a full nonlinear version of those. So for instance, any field that depends on x, now it will be transformed under this transformation. And we want to construct an action which is invariant under that. If we do that, we are guaranteed to get equations that satisfy our original requirement. That we will, I guess we will see it a bit later, why this guarantees that requirement that I erased.
Only the diffeomorphism? No conformal invariance or anything like that?
No.
Right.
Only diffeomorphism.
Why is that?
Because the generator of the translation is T mu nu, he is not considering D mu or the dilation or the special conformal transformation generators. He is only considering T mu nu, which is actually the generator of translations.
Okay, but this goes beyond only translation, right? It can be like whatever coordinate information. Okay, that's fine.
Well, you could. So if you want to talk about conformal transformations, it's you should think of it as the analog of Poincare transformation. So you have theories which are we already talked about Lorentz invariant, Poincare invariant theories. There are some theories which are also conformal invariant. Yeah. So there are you should think of it as a global symmetry. Now,
I thought that invariance is local, can be made local also.
Yeah. Right, exactly. So that's what I wanted to say. You can think of conformal invariance as a global symmetry, and you can make it local, which is now called while invariance. So you can make it local by introducing an additional field in the theory, but that's not what we want to do. So what we want to do is to consider general theory, not necessarily conformal invariant theory, and then couple it to gravity.
Yeah, but the procedure that you're using can be used for other symmetries. That's what.
Yes, yeah, the procedure can be used, but the details will be different. Okay, so now, therefore, our strategy would be to just find the rules to construct these actions which have this symmetry, which are invariant on the general coordinate transformation. Or in general, now I can just say that I want to construct an action which is invariant under x mu going to an arbitrary x tilde mu of x.
You have said that h mu is invariant, actually epsilon is invariant under that transformation of h mu.
Say it again.
You have said that the action of h mu should be invariant under that case transformation of h mu. So how do we know that we don't have to generalize this transformation as well into a nonlinear version?
Yeah, in fact we should do that.
Okay.
Yes, so far I have only talked about the linearized version of the transformation, but then as we go on, we will see that we have to make it nonlinear. So now the one thing that I should mention is that there is some qualitative difference between the case of gravity and the case of electromagnetism. And the qualitative difference is that photons don't have charge. And that implies that you don't need to do any, once we go through this procedure, you don't need to do anything to the quadratic action for photons. That is fine. While gravitons have energy and momentum, so they are actually charged on the translations. And therefore we cannot just keep the quadratic action for h mu nu. They will also, as we saw before, they will also contain energy and momentum, so we have to modify the action also. We have to modify also the part of the action that depends purely on h mu nu, that cannot remain quadratic. This is a bit similar to non-abelian gauge symmetries. There you already, either you already know or you will see in your standard model course that the action for non-abelian gauge theories, they contain nonlinear terms, pure self-interactions of the non-abelian gauge. So you get the Yang-Mills action instead of the Maxwell action. And Yang-Mills action is intrinsically nonlinear.
So will we get interactions between gravitons?
Sorry?
Will we get interactions between gravitons?
Right, exactly. So once we say that gravitons interact with T mu nu, they should also interact with themselves because the gravitons themselves carry energy and momentum. Similarly, in non-abelian gauge theories, you will have a self-interaction between the gauges because they are charged under the symmetry. So therefore, there will be a non-trivial construction of just pure gravitational action and a non-trivial construction of just matter action. Unlike Maxwell theory, in which this part is kind of trivial. But today we want to just focus on the matter action. We want to find the rules to construct this matter action.
What do you mean by this? X mu going to X mu.
Well, we want to construct a theory that is construct an action that is invariant under an arbitrary change of coordinates.
I think he's asking for the meaning of x tilde.
Is that true?
Yeah, I mean, what do you mean by saying that x tilde is a function of x?
Okay, let me give a very... In fact, that's what we are going to do now. So imagine I have so imagine I have an action. So I have the action which depends on this side or depends on the scalar field phi, right? And then I want the action to be invariant under this transformation. What I mean by that is that what is the change of say this phi is a scalar field. What is the change of a scalar field under general coordinate transformation? The change is that phi tilde of x tilde is equal to phi of x, right? Now we can imagine an infinitesimal transformation where x tilde is x say minus x in mu. X tilde mu is x minus x in mu. Then this phi tilde of x tilde is equal to phi of x tilde plus x in mu, right? So we want to interpret this change of coordinates as an active transformation of the field at the same point. So this tells me that phi tilde of x tilde is phi of x tilde plus x in mu d mu of phi of x tilde. So therefore delta phi is equal to x in mu d mu of phi, right? So now I want to construct an action which remains invariant when I implement this change, when I impose this change of the field. Of course, just a second. Of course, this is not the only change that I make. I want to make a set of changes in different fields, and then require that the action is invariant when I implement all of those changes. It might not be invariant under just this one, but everything transforms on the change of coordinates. So once I implement all of those changes, I want the action to be invariant.
When you wrote that the x mu goes to x mu minus a mu, and a mu itself depends on x, and you have written x mu minus a mu as x tilde, right? And since a mu depends on x, that's why x tilde depends on x.
Well, x tilde also depends on
no,
x.
I'm not talking about that. I'm talking about the second last column. Yeah, this one. Since a mu depends on x, that's why x tilde also depends on x.
No, even if a mu is 0, it still depends on x in a trivial way.
Okay, so that's the only thing that he was asking. That y depends on x.
Okay. But did I answer? So what are the rules to construct this action? So remember that before we were constructing actions which are invariant under Poincare transformations. So simpler than these ones. Not general coordinate transformations, but a subset of coordinate transformations. And there the strategy was that we find the scalar quantity and integrate it over the full space-time. That gives us an invariant quantity. So here, at least we want to have that property. So So we need to construct the scalar quantities and integrate them over the spacetime. So, for instance, we have the kinetic term, which has gradient of some fields, and we want to square those gradients using some metric, calculate the norm of the gradient. So before we would write eta mu nu d mu phi, and that was a scalar quantity that we could write as a kinetic term for our fields. It's no longer the case here. This is not a good object, good scalar quantity to put in the action anymore. And the reason is that eta mu nu by itself is not a tensor on the general coordinate transformation. It is a tensor on the Lorentz transformation, but not on the general coordinate transformation. More explicitly, if I find the change of eta mu nu, which is dx tilde mu dx alpha dx tilde mu dx beta eta alpha beta, that is not equal to eta mu nu. So we need a different object, different metric to construct scalars out of vectors or out of gradients of fields. And that other object is g mu nu, which is eta mu nu plus h mu nu. Why? At least y at linearized order in h mu nu. Let us see what is the mismatch between the two sides of this equation. So the mismatch between the two sides is, as you can easily verify, is d mu. So I want to take x tilde mu. Let's see, what did we choose? The minus with the minus. So here we have d mu x nu minus d mu x mu. That is a mismatch between the left hand side and the right hand side of this equation. If I choose this relation, right? Now you see that this is exactly the transformation of h mu nu. So if I write g mu nu in this form, then at least to linear order in h mu nu, what we have is that g tilde. Okay, so now I have worked with, here I talked about upper. Let me actually. If I look at this g tilde mu nu, which is eta mu nu plus h tilde mu nu, we see that it is indeed equal to dx alpha dx tilde mu dx beta dx tilde mu times g alpha beta, which is eta alpha beta plus h alpha beta, up to terms which are of order h. So at least at zeroth order in h, this is a valid equation. Because this mismatch that we have in the transformation of the Minkowski metric is going to be cancelled by the transformation of the h mu nu. Now, at higher orders in h, there will be terms which are higher order linear, at least linear in H, right? Because here, from here, we get terms of order xc times H. Whether or not those terms cancel, they depend on the nonlinear transformation of H mu and nu. By nonlinear, I mean terms which are of order H times xi, or maybe derivatives of H times xi. Those terms we have not specified yet. Once we specify, then it will give us a prescription for how to correct this equation. However, we can take it as a definition, as the definition of those higher order terms, such that this object is actually the full story. This is a tensor. So this by the requirement that this equation holds at all orders in H, not just at zeroth order. That requirement can be translated into the specification of what are those higher order corrections. So that's we take as our definition of what we mean by H mu nu, or transform, nonlinear transformation of H mu nu. So now, therefore, we have a tensor, and we can also find the inverse of this G mu nu, defined by. So this is G mu nu inverse with upper indices, and it's defined as the inverse of G mu nu. So G mu nu, G mu sigma is going to be delta mu sigma. So what we can do to construct invariant actions is to replace, wherever we were using eta mu nu, we know we want to replace it with G mu nu. So eta mu nu by itself is never going to appear anymore. Also H mu nu is never going to appear because eta mu nu is not a tensor. Since eta mu nu plus H mu nu is a tensor and eta mu nu is not a tensor, it means that H mu nu is not a tensor. So in the action, we never have eta mu nu or H mu nu separately. They will come together as the measure. So this is the rule number one. We construct the action out of G mu nu and the matter fields. The second rule is to so this was the story of the metric. Of course, we have already seen an example of this in the case of a point particle. When we coupled the point particle to H mu nu, we saw that at least a linearized order we can combine eta mu nu and H mu nu into this object, into G mu nu, and write an action which only depends on G mu nu. Now we are saying that should be the full nonlinear form of the action, not only valid at linearized order. And therefore, the geodesic equation that we derived from that action, now you should think of it as the full nonlinear equation for the motion of particles in a gravitational field. So now the next thing to talk about is to talk about the derivatives. In particular, the derivatives of vector fields. So when we work with just Lorentz invariant, when we try to construct just Lorentz invariant action, if we have a vector field like a mu field, we use the normal derivative of that. And this is a tensor if I'm under Lorentz transformation. However, this is not a tensor on the general coordinate transformation, because if I do a transformation of this, if I look at this object dx alpha dx tilde mu, d alpha dx beta dx tilde mu a beta, this is not equal to dx alpha dx tilde mu dx beta dx tilde mu of d alpha a beta. There's an extra piece that comes from acting by derivative on this transformation matrix. That used to be just a constant in the case of Lorentz transformation, so it would go up. But now you're considering general coordinate transformation, and now it won't go out anymore. There will be a derivative of that. In fact, this is something that you have probably seen examples of it when we work with curved coordinates, even in flat spacetime. We don't need to go to some curved spacetime to see the fact that derivatives of vectors are not tensors in general. This is just the fact, an artifact of vectors at different points not being comparable. Say, for instance, if we consider polar coordinates, then so just on a plane we can consider polar coordinates, in which case we have the r and theta components. Of a vector field. So if this is our A, there will be a r and a theta. And when we take the derivatives, we are just comparing components of vectors at different points. But a theta, for instance, or a r, at different points, point in different directions. So these are not really comparable objects with each other. So taking just ordinary derivatives of components of vector fields is not going to give us valid tensor fields, even in the curved coordinates in flat space. And one can fix it using a metric. Once we have a metric, we can construct objects which are called covariant derivative, which give us tensors out of vectors, or higher rank tensors out of lower rank tensors. So, for instance, you have probably seen the examples, the explicit examples in particular cases, like in the case of polar coordinates or spherical coordinates. Like, for instance, when you write Laplacian in the polar coordinates, this is the divergence of this vector. Now, okay, so we are in 2D. Let's use just R. And if I want to write this Laplacian in polar coordinates, it would not look as just taking second ordinary derivative. it will look like 1 over r dr of r dr of phi plus 1 over r squared d theta squared times phi. So what we do in order to construct this covariant derivative is to use component of metrics. In this case, the metric is given by dr squared plus r squared d theta squared. And the way we construct this covariant derivative or covariant Laplacian is to use the metric to construct, say here for instance, to construct a tensor and then take the trace of that tensor. So now this can be done generally. Doesn't have to be just done example by example. There is a general prescription which is to construct the following object: gamma mu alpha beta, which is called the Christoffel symbol, and this object by itself is not a tensor. It has 3 indices, but it's not a tensor. But it is non-invariance, or this mismatch from being a tensor is exactly such that when we combine it with ordinary derivatives in the right way, it allows us to construct a tensor. So this gamma mu alpha beta is something constructed out of derivatives of the metric in the following way. Yes. And now we can use this to construct a covariant derivative of a vector field, which is obtained by combining the normal ordinary derivative, which is not a tensor, with the right combination of gamma and a. So gamma alpha mu nu ar. Now you can check that this object is not a tensor. It's kind of easy to guess why, because it's made of ordinary derivatives. And this is not a tensor either, but the combination is yes.
Is it unique, this?
Is this unique? No, it's not unique, because you can add to it any tensor, any rank 3 tensor, and that will also do the job. Or you can also say it in the other way. If you have 2 of them, if you take a difference, it has to be a tensor, because the mismatch has to have a very particular form. Yes?
Saying that in the textbooks they use a plus sign between the 2 terms in the covariant derivative. So does it matter?
No, this is the standard definition. What you have seen is the derivative of contravariant vector.
Okay.
So that there the sign changes. So in general, if you want to construct the derivative of a general tensor with many indices, alpha 1, alpha 2, etc., beta 1, beta 2, then we can again do that by a combination of this Christoffel symbol, so we have the ordinary derivative. And then for every upper index, contravariant index, you will get plus gamma beta 1 mu lambda t lambda beta mu. And then it continues for all betas, and then minus gamma lambda mu alpha 1 t lambda alpha 2 beta 1 beta 2, and then it continues also for all lower indices. So for every index there is one of this.
Actually, where I saw these plus sign, they were also calculating the covariant derivative of the covariant vector, but the reason because of which they have a minus sign is that the signature was different.
I don't think so.
Yeah, because for example in R2 and Weber they have a plus sign for while they are calculating the covariant derivative of a control for covariant vector.
Okay. You can obviously define it to be minus whatever. And then the sign changes. But I think this is relatively standard. The signature doesn't change because it's quadratic in the metric. Okay, so that's it. We don't use ordinary derivatives, we use covariant derivatives. So this is rule number 2. The matter action is made of G mu nu, its inverse. Psi is covariant derivative, and maybe higher order covariant derivatives. Obviously, psi can be also a vector field. Now we know how to take its derivative. Finally, the third rule is it's regarding the volume element. So we construct the action by integrating it over the full space-time. So we write, for instance, the measure of the integration is d4x, but this measure under general coordinate transformation, it changes by the Jacobian of the transformation. So this becomes this is equal to the Jacobian of this transformation, dx mu dx tilde mu times d4 x tilde, which is obviously not equal to d4 x tilde. So we construct an invariant measure which can then be multiplied by a scalar Lagrangian to give us an invariant action. How do we do that? We notice that again we can use G mu nu. We notice that G mu nu is a tensor. So if I take the determinant of G tilde mu nu, that is equal to, since there are two indices, two transformation matrices here, that will be equal to the Jacobian of the transformation dx by dx tilde the squared times determinant of G mu nu. So if I combine, if I look at d4x times the square root of minus g, where g is defined as the determinant of G mu nu, and where minus is here because we have we are in Lorentzian signature, so the determinant of the metric is negative, so minus makes it positive. If we construct this object, then this is going to be invariant. the Jacobian that comes from the change of the measure cancels from the Jacobian that comes from the change of the determinant of the measure. So therefore we have all of the rules. We write an action which is d4x, the square root of minus g times a Lagrangian, which is a scalar made of g mu psi and the covariant derivative. Maybe higher order covariant. You could also think about it from an active point of view, active transformation point of view. So there, the way I justify the addition of this square root of g was from a passive point of view in which I changed the measure. You can also think of this transformation as being just the transformation of the fields, not coordinate. And you will see that now, from that perspective, L is a scalar quantity. So under coordinate transformation, it changes to xi mu d mu of L. So if this the square root of g wasn't there, the action wouldn't be invariant. But once the square root of g is there, if we include the change of the square root of g, then the sum of the two becomes the total derivative. Just keep in mind that you can use both ways. Sometimes one way is easier to think about it, sometimes the other. But the action is invariant both. Either if you think about this coordinate transformation as an active transformation or as a passive transformation.
Are they the same physically? I mean, the active and the passive. Does that have any physical implications?
No, they are physically the same, just different ways of labeling the points in the space-time. Active means that you keep the same labels and you change the fields. Passive means that you also change the labels. I don't think there's anything deeper about it. So what else? I guess. Oh yeah, so one thing that is important to mention, so we achieved part of our goal, which was to construct a matter action which is invariant under general coordinate transformations. We find the rules how to do that. Of course, it remains to see why it accomplishes what it was supposed to accomplish, which means that to give us a consistent theory for the interactions of this spin 2 particle. In particular, with the fact that it gives us the same linearized theory that remains to be checked after we also construct the gravitational part of the action. But one thing to be said already here is that so now we construct a theory which is invariant under this general coordinate transformation. Now we can notice that we can always choose at any given point, say x naught, we can choose or perform one of this coordinate transformation to make metric to be Minkowski metric, and to make its derivative to vanish at that particular point. This is very important. This is called the equivalence principle.
But not the second derivative.
Not the second derivative. The fact that this is positive is not that hard to see at a single point. So again, the transformations of G mu nu is this, and now I want to require that this G tilde at some particular point, let's call it point x equal to 0. I want to require that this G tilde at x equal to 0 is equal to eta mu nu. I can always do that, find this matrix. So let's do the following. Say that I want x mu to be given as an expansion in terms of x tilde. So it's given by some a mu alpha x tilde alpha plus some b mu alpha beta x tilde alpha x tilde beta plus higher order terms. So that at x equal to 0 we so at x equal to 0 we get some linear relation. So this higher order tends to become important as I go away from x equal to 0, but at x equal to 0 this is the most relevant part. Now this, and these are constant coefficients. Now, so this G alpha beta is a symmetric matrix. Let's think about G alpha beta at point 0. That's a symmetric matrix. I can always diagonalize this symmetric matrix, and also I can find the transformation, matrix A, to make the norm of those diagonal elements to be 1. So that fixes this A mu alpha. It fixes it, of course, up to a Lorentz transformation, because we know that once we make the metric to be eta mu nu, then it is still invariant on the Lorentz transformation. So up to Lorentz transformation, this requirement fixes this coefficient. There are enough free coefficients here to perform this. And then these p's can be fixed so that the first derivative is vanishing. But we cannot make all of the second derivatives to be 0. This means that as long as we are dealing with a small, in some gravitational field, so remember that this G mu nu is what captures the effect of the gravitational field. H mu nu is inside G mu nu. When I say that I can choose a coordinate system in which G mu nu is eta mu nu and its derivative is vanishing, it means that that is a coordinate system which is closest to being in the absence of gravitational field. In particular, if I'm doing very small scale experiments, or I have a good clock whose internal dynamics is much smaller, or time scale much shorter than the scale of variation of the field, those work as if there was no gravitational field. That's why these frames are called, these coordinate systems are called locally inertial frames.
It also means that in that frame the Christopher symbols will vanish.
Yes.
But their derivative will not vanish.
Right.
And can you say that since the derivative of the Christopher symbols are not vanishing, that's why the intrinsic curvature is not 0? So the Riemann tensor is not 0.
Yeah, that's one way. I mean, it can be 0, but it doesn't have to be 0. But I guess the other way of thinking about this, that the curvature tensor that we are gonna talk about it later is a tensor. It's an invariant tensor. You cannot do a coordinate transformation to set a tensor to 0, because if a tensor is 0 in one coordinate system, it has to be 0 in all coordinate systems.
And using this statement of yours, we can also establish that since Christoffel symbols are vanishing in this coordinate system, therefore they are not tensors.
Yes.
If it's 0, so we can transform G according to X to Riemann if the Riemann tensor is 0. So
If the Riemann is 0, then what?
we can transform the G into Riemann with general coordinates or something.
So at a single point, you can always do that. But if it is 0 everywhere, then yeah, you can do it global.